exponential functions and their graphs. So exponential function f of x equal to a to the x. Now a here, this number a is the base. It's a fixed positive real number. Okay, it's not equal to 1. That's a boring exponential. 1 to the x would just be, some horizontal line passing through 1. Okay, we're talking about an exponential function here. If ever there was a time for exponentials to be important, now's that time. Talking about the growth of this COVID virus is growing in an exponential fashion. Okay, I don't know if you watch the news, but every 2 to 3 days the amount of cases doubles. That's exponential growth. All right, so applications. Tons of applications for exponential growth. Okay, one of my applications is the spread of epidemics. So they're trying to model the death rate of eventually what's going to happen right now. They're using exponential to do this. Compound interest is another. Compound interest is earning interest on your interest. Okay, big deal in the stock market, which is also in the news right now. Population growth. Okay. You think about population growth, the more people there are, the more people they have. So the bigger the population, the faster the population grows theoretically, right? Till there gets to be some overpopulation in some areas, and then crazy things happen. Viruses or whatever develop and, kind of level off the population. Some overpopulated areas is kind of Mother Nature's way of taking care of things. Also radioactive decay. It's another application for exponential functions, okay? So let's talk about the domain and the range of exponential functions. So the domain, any number I plug in needs to spit out a real number. The domain for exponential is negative infinity to infinity. So all real numbers, or R if you want to just put R. The range typically, as long as we don't shift it up or down, is R positive. What is that? That's from 0 to infinity, not including 0, not including infinity. All positive real numbers. Okay. All right. So the example that we're going to run with f of x equal 2 to the x. Okay, so what I'm going to do, I'm going to start with the table x and 2 to the x. So -3, -2, -1, 0, 1, 2, 3. What is 2 cubed? That's 8. What is 2 squared? That's 4. What's 2 to the 1? That's 2. What's happening each time? I take 8. To get to 4, I divide by 2. To get to 2, I divide by 2. To plug in here to the 0, what I do, I take 2 and divide by 2. 2 divided by 2 gives me 1 here. Okay, what about 2 to the -1? Well, 2 to the -1, I take 1, I divide by 2 again, right? So that's 1 over 2. I take 2 to the -2, what's going on here? Take 1/2 and I cut that in half, that's 1/4. And 2 to the -3, remember this is exponent rule, says this is 2 over 3, which is 1/8, okay? So what's happening as I get more and more negative, my answer is getting closer and closer to 0. Okay? So let's graph this, see if we can get a better idea of what's going on here. All right. So 1, 2, 3. 1, 2, 3. So when x is equal to 0, I get 1. When x is equal to 1, I get 2. When x is equal to 2, I get 4. When x is equal to 3, I get 8. And so I'm already shooting off the page. Okay, it's growing up exponentially. So 0, 1, that's an important point there. That's where we're crossing through with this. Okay. Now, when x is negative 1, I get a half. When x is negative 2, I get a fourth. When x is negative 3, I get an eighth. And you can see it doesn't take long for this thing to get really, really, really close to the x-axis. Okay? So when you're talking about the domain, it's all x values. Your domain is from negative infinity to infinity. That's the domain. The range, well, we never get to 0, but we get really close to 0, and then we go up. We're going up to positive infinity, right? So the range is from 0 to infinity here. Okay? We call this when the base is greater than 1. Okay, this is an increasing function. It's increasing. That's exponential growth. So you might be asked, is this an exponential growth function or exponential decay? If the base is greater than 1, it's an exponential growth. So let's state that. If a is greater than 1, then f of x equal to a to the x is exponential growth. Okay, exponential growth. You see that? We're growing over time. We're increasing. Okay. The number of cases every couple of days of the coronavirus, COVID-19, is growing exponentially. Every 2 to 3 days, the amount of cases doubles. Okay, that's an exponential growth. Right? Maybe, you start at 1, then the next day you have 2, the next day after that you have 4, or the next day after that you got 8, and so on. It just keeps shooting up and up and up. Okay? At some point, there's some leveling off, and that's a special type of exponential, but we're not going to talk about that type in this course. Okay, it's a little beyond the scope. All right, more of a logistic curve. So we've talked about exponential growth, okay, and we have a horizontal asymptote here. The horizontal asymptote is y equal to 0. Okay. You think about it, if the further out you plug in x negative numbers, okay, so like if I had like x equal to negative 1,000, 2 to the negative 1,000 would be 1 over 2 to the 1,000, which is basically 0. It's like 0.0000000, a lot of zeros, and then some decimal. Okay, it's really close to 0, but it's not equal to 0. Okay, so let's talk now about exponential decay. Okay, well, actually, let's talk just a little bit more. So this is an example. 2 to the x is exponential growth. What if I had a curve like g of x equals 3 to the x? 3 to the x means it triples every day. Okay, so instead of doubling every day like this one does, this one triples every day. So it's going to be growing even faster. At day 1 or at day 0, there's just 1. But then day 1 here, there's 3. And day 2, there's 9. And so it just shoots up super fast. Okay, so that's 3 to the x versus 2 to the x. Okay? Now the flip side of this is it shooting up faster this way. It's going down to the x-axis faster on that side. Okay? So when you're comparing graphs, say you had something a little bit less than 2 doubling. So maybe like some h of x that was like 1.5 to the x. Okay? This one would be growing a little bit slower, but it's still growing, right? So 1.5 R naught factor going through like this, and it's higher on that end. Okay? So as you adjust the level, okay, so as you adjust the base, make it bigger or smaller, it's going to either make it steeper or make it less steep. Okay? So the higher that base, the bigger it is, the more steep that it gets. The closer it is to 1, the less steep that it is. Okay? So hopefully that helps you out. All right. Let's now talk about exponential decay. So if a is between 0 and 1, then f of x equals a to the x. This is exponential decay. Okay, exponential decay. That means the function is decreasing over time. When I looked at this one, I'm going up over time, right? That's exponential growth. That's good, especially when we're talking about like your money in the stock market or whatever you have growing. You want it to be growing, not decaying over time. Right? So exponential decay would be a scenario like this. My graph is doing something like this. It's literally flip-flopped. Okay, we're still passing through this 0, 1 here, but now it's flip-flopped. The domain and range are still the same, negative infinity to infinity, and the range is still 0 to infinity. It's just instead of going exponential growth, we're now decaying over time. As x increases, what's happening to my f of x? My f of x is going to 0 over time. So I still have a horizontal asymptote, y equal to 0. Okay? So, an example you might have here, you might be given, some graph. Let's do... Let's do f of x equals 1/2 to the x. Okay, so my base is less than 1, greater than 0. So I pass through here. At x equal to 1, that's 1/2. At x equal to 2, it's 1/4. X equal to 3, it's 1/8. Okay, and then the reverse here, 1/2 to the negative 1. This is 1 over 2 to the negative 1, which becomes 2 to the 1. Exponent rules. We flip negative exponent, do the reciprocal. So this is 2 here, and then 4. And so it literally, we took the graph and we reflected it about the y-axis. Okay, so this graph is the reflection about the y-axis. All right. This here, this is 1/2 to the x. What if I did You know, what if I did like instead of 1/2, I did 1/3. Okay, 1/3 maybe. So h of x equals 1/3. So this is a smaller base. That smaller base, okay, is actually going to be going down to 0 faster. Okay. So you think about it. If I take somebody's height and I half them every time, so you got somebody and you cut them in half. Oh, that kind of disappeared them. Okay, so you cut them in half, right? They still got half their body left, but that's more than what they would have had if you cut them into a third, right? They'd only been up from the knees down, right? So when you 1/3 something, it's going to 0 faster, okay? But if it's going to 0 faster, then it's actually getting faster on this end. So that's 1/3 to the x here. I'm just giving you comparisons. And then say instead of like 1/2, maybe it was 3/4. 3/4 to the x. This is growing slower on this side, and it's getting down to the x-axis slower on that side. Okay? So as you adjust your base, the numbers between 0 and 1, the closer you are to 1, the more flattened out your curve is. And the closer you are to 0, like 1/3, 1/4, whatever, the more steep your curve is. Okay? All right, so best thing you can do maybe for you is to just graph it. If you're having trouble picturing it, you go to your calculator, type in, maybe you want 2 to the x. So I graph that and I look and I see, okay, it's an exponential. If I want to see the table, get some number values to plot points, you might be asked, do second table, and then you can see as many points as you want to plot there. You know, it's up to you what you want to plot. Okay. Same thing with if I had like 1 divided by 2, parentheses, to the x, hit enter, and now you can see that's the reciprocal, right? So we literally took a function and we reflected it across the y-axis. Okay. So let's try to do a little bit of what we did in the first week of class. So let's do a little bit of review here. Recall a to the x times a to the y. Same base, what do? We add the exponents. Okay, we add the exponents. What if I had a to the x divided by a to the y? Okay, I subtract the exponents, x minus y in the exponent here. All right, what about power to a power? Power to a power, I multiply exponents, right? And then say I had like a over b raised to the x. Everything in the parentheses gets raised to the x. Okay? So you need to be able to not only go one way, but you need to be able to go the other way as well with these rules. So we got to be ninjas when it comes to using these old rules that we learned at the first of class. Okay? So you got to think back a couple of months, but you can do it. Okay? So, you know, sometimes you're dealing with functions. F of x equals -2 to the x plus 1. You know, if you need to graph it just to kind of get an idea of what the transformation is going on, I'm not going to look down on you because of it. Go in here and just graph it and see what it looks like. So it's negative, and then you got what? 2 to the x. And then what? Plus 1. Okay. So look at that graph there. It looks like my graph got flipped. It got reflected. So it reflected across the x-axis, but then I shifted the whole thing up 1. Okay, so you know, remember, use your order of operations. Please excuse my dear Aunt Sally, right? When we're doing our transformations. Really, the parent here is 2 to the x, which we know 2 to the x looks like this here. Oop, not a line. So that's what my 2 to the x looks like. All right, it passes through this point, 0, 1. That's a point I will want you to mark on your scratch work. Now, multiplying your function by negative flips it across the x-axis. So now all of a sudden, we're passing through this point, 0, negative 1. But then what happens? What happens here? I actually get shifted up 1, right? So I shift up 1, vertical shift up 1, and so now my graph looks like this. So I literally shifted up 1, and it crosses through at that 0, 0 for my intersection there. Okay, so that's what's going on with this graph here. All right, so kind of give you a way to look at it from both sides, looking at it through graphing it versus using tools for transformations. Okay. That maybe I'll show you one more and then we'll end this video and we'll talk about a new concept. F of x equals 1/2 to the 1 minus x. Let's use some properties of exponents. This is what? This is 1/2 to the 1 times 1/2 to the negative x. So 1/2 to the 1 I can't do anything with, but this is 1 to the negative x over 2 to the negative x. Now 1 to the negative x, that's just 1. Okay, doesn't matter what I plug in my exponent there, it's still 1. And then I have 2 to the negative x, but negative exponents, if I flip up, do the reciprocal, I can get rid of the negative exponent. So I get 2 to the positive x. So what do I have? I've got my function f of x equal to 2 to the x, but I also have this 1/2 factor. So it takes my graph, okay, which is like this, and it passes through 0, 1, and then it cuts it in half. So now every value is closer to the x-axis. It's still going up, it's just not going up as fast. It's half that. Okay, it's half that. All right, so any value you pick, like if this is 1/2 here, then this value here is 1/4. It's literally half of that. If this value is 8, then this value is 4. That's what the halving does. It cuts your value in half. All right? Okay. So let me change the color here just because it's fun. All right. Hope that video helps you kind of understand the basics behind exponential growth and exponential decay. Okay, the big thing here, remember growth, your base is greater than 1, and exponential decay is between 0 and 1. Okay, all right, good luck.